I was sitting, writing on my textbook, but the work did not progress. My thoughts were elsewhere. I turned my chair to the fire and dozed. Again, the atoms were gambling before my eyes. This time the smaller groups kept modestly in the background. My mental eye, rendered more acute by the repeated visions of the kind, could now distinguish larger structures of manifold conformation. Long rows, sometimes more closely fitted together, all twinning and twisting in snake-like motion. But look, what was that? One of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes. As if by a flash of lightning I awoke, and this time I also spent the rest of the night in working out the consequences of the hypothesis.
These were the words of Frederick August Kekule, a Belgian scientist who 7 years before had had a dream where he realised that the benzene molecule had a circular cyclic structure rather than a linear one, like many of the other organic compounds that was known at the time. Michael Faraday had discovered benzene in 1825, and for years people struggled to propose a structure that made sense. There just seemed to be too much carbon for the hydrogen in there. They couldn't create a structure that worked. And it wasn't until 1865, when Kekule had had his crazy dream about a snake biting its own tail, that it just seemed to make sense.
So here we are again with Kekule's structure. Now, it was an improvement on anything else that they proposed, but it still has some issues with it. Okay, there are three kind of problems with it. One is its shape, okay, all to do with its bond length. The other is to do with stability. And the other one is the reactivity. So I'll start over here with reactivity. Now, we know from our alkenes topics that we've studied that alkenes like to undergo electrophilic addition. So if I had cyclohexene here, and I reacted this with some bromine, I would quite rightly expect to make a dibromo cyclohexane, and our bromine adding across the double bond. So if we had our triene, okay, our cyclohexatriene here, we would expect that 3 bromines would react across and give us this weird hexabromo cyclohexane thing. Now, it doesn't. Okay, basically this doesn't happen. So the reactivity of benzene is different to the reactivity that an equivalent alkene would have. Okay, now that is kind of linked in to the stability. Okay, it's more stable, it won't undergo those reactions. Now, using a simple model, this cyclohexene we could hydrogenate with hydrogen and a suitable catalyst, be it nickel, platinum or something clever, to turn it into the cyclohexane. So if we had 3 of these, we would expect that this reaction would have 3 times the enthalpy of the first one. Now, this first one is minus 119 kilojoules per mole. Okay, that's the enthalpy change for that reaction. So if we're doing 3 lots of this, so breaking 3 double bonds and replacing them with more, 6 CH bonds, then we would expect our value for this to be minus 357 kilojoules per mole. But what we find with benzene is, so benzene, and we hydrogenate this, then the value is minus 208 kilojoules per mole. So less energy is given out. Benzene is more stable. And in fact, it is 149 kilojoules more stable. And that's something important to put in any exam questions, because they do like this sort of idea. Put this in your answer somewhere. Okay, I'll just show this in a different way. So here I've got an energy level diagram, and we're going to imagine I'm starting up here with our 135 cyclohexatriene. Okay, if I write it down, 135 cyclohexatriene. Now I'm going to add some hydrogen to this to turn it into a diene. Okay, so I'm adding hydrogen across one of those double bonds, and this would have released minus 119 kilojoules per mole. Okay, so that's one step. I then add another hydrogen, leaving me with a single double bond in there. That would be another 119 kilojoules per mole. And my final step, to fully hydrogenate, to turn it into cyclohexane down here, that would be another minus 119 kilojoules per mole. So this whole journey down here, top to bottom, would be minus 357 kilojoules per mole. Now what we find is benzene, and I'm going to show benzene over here in this format, which I'm conscious I haven't discussed yet, but you have probably seen it around in textbooks or in questions and things like that. This hydrogenation, so this time I'm adding 3 hydrogens to get it all the way down in one go, we find is minus 208 kilojoules per mole. So it's starting from a lower energy point. Okay, so we're all trying to get to the same energy down here where the cyclohexane is. So because this enthalpy of hydrogenation is a lot less than the total was for the theoretical triene molecule, it must be starting from a lower position. It is more stable. So remember, the lower energy is greater stability. So this is more stable. So what did I say it was? It was 149, wasn't it? 149 kilojoules more stable. Okay, so this energy diagram hopefully can just sort of demonstrate that. So going back to the final point of this, so the other reason why it doesn't quite match up to our theory is the bond length. Now, carbon-carbon double bonds have a bond length, so the distance of the size of that bond is 0.134 nanometers. A single bond is slightly longer, 0.154 nanometers. So if this was the case, our molecule here, now we'll exaggerate this, is going to have a long single bond, a short double bond, a longer single bond again, a short single bond, a long double bond, long single bond. I've got all mixed up here, I don't even know what I'm saying. You get the idea. So it's going to have this asymmetric kind of shape about it, and it is, we know what they look like. We know they are symmetrical. The bond lengths are all the same. It's a symmetrical molecule, and the bond lengths are actually 0.140 nanometers for each of them in benzene. this is some evidence for the fact that the bond lengths are all the same. So this is a process called scanning tunneling microscopy, and we can sort of see how our benzene ring is in here, our carbon ring that we go around, our hydrogens will be stuck out on the limbs over here, and it's a nice symmetrical structure. Okay, so there we have it. That's the structure of benzene, and what I will sort of do now is go on to the reasons why our model that we use currently is slightly different to this. So, why is benzene more stable? I'm going to go back a little bit on this one, and we're going to look at just a double bond. So a double bond, we have two carbons, and they have orbitals that overlap between them. Excuse me, shocking drawing there. Okay, so that's a pair of orbitals between them. Now, if you remember, or if you've studied alkenes, you might know they are sp2 hybridized. If you're not sure about this, go and have a look at my video on hybridization. So this, between the axes here, would be a sigma bond. That's a really terrible sigma bond. Now, in addition to this, each carbon has a leftover p orbital which sort of sits above and below the carbons like this, and they line up. So these p orbitals are in the same plane orientation as each other, and what can happen is these overlap to form pi bonds, and this is what forms the double bond. Okay, and it's this idea that we're going to use in benzene. So I'm imagining now I'm going to be slightly side on. Okay, so we're going to look at our benzene kind of angled on or something like this. Okay, and because on each of these carbons here there is a p orbital, and if we imagine our double bonds, they're going to be alternate, so above and below. These are not two bonds, it's just one bond between those two, between those two, and between those two. And what can happen is, because all these p orbitals, which then form pi bonds between them, they all line up and they're in the same orientation, the electrons can become delocalized and flow around all of the atoms. Okay, it's a delocalized electron ring, and this is the principle of why they're more stable. Okay, it decreases the energy of this system. Really, really fundamental, and this is why we show our benzene with a circle in the middle. Okay, this represents our delocalized ring. Now, I have seen questions where you've had to apply this idea of increased stability when we get pi overlap in the past. So if we have a molecule like this, and we're going to compare it to a molecule like this, you might say that one of these is less likely to undergo addition or something like that. I can't remember the context of the question. But we can get electrons moving, we call it conjugation, where things can move around. So because on each of these carbons the pi orbitals are in the same orientation, the same plane, these electrons can kind of flow through the system into the sort of adjacent orbitals on the next carbon, and they're moving around. And this is just like a kind of a mini, we call it aromatic, which is why benzene's called an aromatic compound. Aromaticity, maybe? There we go. I don't know, am I making this stuff up? I don't know, probably. But these things, when we get these alternating double single bonds, we can get this overlap of p and pi orbitals, and it allows the molecules to become more stable. Okay, so just to sort of summarise this in one word or two, the bond length. Why is the bond length in benzene the same? So why do we form perfect hexagons essentially with it? This is because the electrons are delocalized around the ring because of the way that the orbitals kind of line up. Okay. Why is benzene more stable than we would expect? So the theoretical 1,3,5 cyclohexatriene. Okay, why is it more stable? Well, these delocalized electrons give it more stability. It takes it to a lower energy level. And likewise, our reactivity is all linked into that as well. Okay, it's less reactive, less prone to electrophilic addition. Okay, we don't get addition reactions going on because it's already more stable. So key bit, okay, we've got these delocalized ring of electrons. Next time I'll move on to probably naming them, I think, because that's a bit of a can of worms. Okay, bye.